Welcome back! In the last episode, we learned what kind of data types are in the C language and how we can use them. To get familiar with the library that handles peripherals, it is necessary to introduce additional C language keywords. These are the Struct, Typedef, Enum, weak, and volatile terms.
A structure in C is a composite type that is a type that contains additional variables and even additional structures. These are called fields of the structure, and the user can specify what the fields should be. A simple generic example of a structure is a register of users. As you can see in the example, the name of the structure must be given after the struct language keyword, followed by the fields between braces, and the definition must be terminated by a semicolon. The member variables are arranged in memory in sequential order. The fields are defined in the same way as the variables. Instantiation of the struct user variable and access to the fields looks like this. To access the fields of the initialized structure, the name of the field is written after the name of the instance, separated by a period.
You can use the Typedef keyword to refer to existing types by a new name.
You can even give a new name to built-in types such as char, as well as to structure types that you create, avoiding having to write out the struct keyword every time. In the case of structures, the redefinition of the type can also embed the definition of the structure. In this case, the new type name must be given after the braces but before the semicolon. The enum is a language element used to create a special type. It is usually used in cases where the stored information requires little memory, can be easily described, and is not overly verbose.
An example for that is the state of a state machine or a switch that affects the operation of something. In these cases, we could write a perfectly correct code if we represented the states or switches by integers, since the states of our state machines are countable and finite.
In such a case, however, the readability of our code would be greatly impaired, and so would our own efficiency, since we would have to remember exactly which state corresponded to which number, and debugging would become a nearly impossible task. This is solved by the enum type, where we can specify the possible values in an enumeration, and the compiler counts and treats them as integers. In the code, we can refer to the values of variables by their names, so that our program remains traceable and transparent. For example, if our task is to control a gate, and the state machine needed to do this has 4 states, then this way we can create an enum variable.
The Extern keyword allows you to separate the definitions and declaration of your variables.
Let's say you have a global variable that you have previously created in one of your project's .c files. If we want to access it from another .c file, we cannot do so by default because of the missing declaration. The solution to this problem is to include the variable you want to use in your code in a similar way to the definition, but add the extern keyword before the variable declaration. This method is used to declare the variable, which should be thought of in the same way as for functions. To understand how it works, let's look at a simple example. In the 1.c file, we have defined a variable called counter. In another source code called 2.c, we refer to it as an external variable and increment its value.
Use the weak attribute to tell the compiler that the function is weak. But what does it exactly mean for us?
Such functions basically have a default definition, but this operation can be overridden by a function with the same name, type, and parameters. The compiler checks if there is a non-weak function definition, and if so, it will compile it into our program. Such an operation is used to implement peripheral interrupt handler functions, for example. So the user only needs to write them if he wants to achieve a different operation than the default.
C compilers have a wide range of optimization tools. The GCC supports more than 100 optimization methods that can be enabled individually.
One of the simplest optimization steps is that if a variable has already been loaded from memory into registers, it is not necessary to read it from memory again on the next readout, as long as its value remains unchanged. Since optimization is done during the compile time, the compiler also tries to determine during the optimization time whether a variable's value has changed since the last read, but this is not always possible. The contents of the memory addresses that represent the peripheral, which, for example, give the logical values read from each pin of an input port, don't change value as a result of the program we wrote, but because of the changes in the outside world.
At compile time, it is also not possible to determine if some variables might receive a new value in an interrupt or via an indirection, which is a pointer. When such optimization is used, the volatile keyword ensures that a variable is read from memory at each occurrence.
The volatile keyword is specified at the declaration of the variable with the following syntax shown on the screen.
This introduced us to the most important C data types, implicit and explicit conversion between each other, and a few other keywords. We did all this to be able to use the standard library mentioned at the beginning of the chapter. Well, now the time has come.
ARM provides the CMSIS, that is the Cortex Microcontroller Software Interface Standard Library for developers, to access the hardware. Since it is developed directly by ARM, the library is uniform and can be used with all supported Cortex-A and M cores, regardless of the specific microcontroller manufacturer. The CMSIS library consists of several interdependent parts. Now, we will take a look at the core M part. This part of the library contains a header file for each supported controller, in which the memory addresses of the hardware controller registers are defined according to the memory map.
For example, the GPIOD I/O port control registers, in our case for the STM32F446 board, are defined in the STM32F446XX.h header file.
There are 9 registers in total for each I/O port on this microcontroller, and they are arranged in memory one after the other. Since these 9 registers are logically related, CMSIS organizes them into a common structure. Note that all registers are supplied with the volatile keyword via the I/O macro.
With this structure, you can now access all the settings for port D, as well as read and write if it is set to digital I/O.
However, if this was all the support that the library provided, we would still have to dig out a lot of information from the datasheet, since we don't know exactly how the bits in each register affect the operation of the device. Another library that uses CMSIS, one level higher than CMSIS, is the HAL, by full name Hardware Abstraction Layer Library. This library simplifies further the handling of peripherals, but this will be discussed in detail in later video chapters.
In this chapter, we learned about the differences between architectures and the evolution of programming, reviewed the process of compiling and how it works, and finally introduced the standard libraries and other language elements. The later parts of the curriculum build heavily on programming knowledge, so I hope you will find useful what you have learned here. In Chapter 4, you will have the chance to test your knowledge out, since you will get to know the programming environment and we will write our first code together. Thank you for watching us. See you next time.
Bye!